All right, everyone. Today we're going to look at Unit 3, Lesson number 6. It talks about connecting similarity to transformations. The big key today is to understand what exactly does it mean for figures to be similar, and um, for what do we know after that? Well, um, figures that we've been talking about dilations, figures that are dilated are automatically similar to each other, right? They have the same shape, but they have a different size. For instance, in this case here, we see a triangle ABC, and we see another triangle DEF that is an enlarged version of it. Now, if we did this by a transformation, this would be A prime, B prime, C prime, but we're going to skip over that right now. But if we know that they're similar, all three angles must be the same. One, two, and three, and all of the side lengths have to be in proportion to that dilation based on the scale factor. So in this case, they tell us here the scale factor is 1 to 2, meaning that the original would be a size 1, the and would be a size 2. So we would call this a scale factor of 2. Think of this as 2 divided by 1. Right? That's kind of what it is. We multiply by 2. So when we see a side length of 8, the end result will be 16. Right? Now if we know it's similar, then we know the other sides are going to have to match up as well. So we're going to need to learn how to again um, check this consistency, make sure all the angles are the same, make sure all of the side lengths are in proportion, and then we will work on making a similarity statement. Is very similar to making a congruent statement, but congruence implies that it's the same shape and size. Similarity just is the same shape. So a question might be something along the lines of, are if these two triangles are similar, write a statement of similarity, right? So let's look at the two triangles here. So we have RST, we have 76-degree angles with a 28-degree. We see the same thing with the other one. We see side lengths here of 10 and 5. We see side lengths here of 2 and 1, right? So that is the same proportion, right? So again, 10 to 5 is 2, 2 to 1 is 2. Again, we could also think to go from one to the other, we are multiplying by 1/5, right? And that kind of holds for each one. So how do we make our similarity statement? Notice that we're using just like a tilde. We're not using the tilde and the equal sign. Just keep that in mind. This is a similarity statement. So it says go from R to S, and then from S to T is our name here. So we're going to go um, down the short side and then down a long side, right? So we've got some flexibility here because of the way the angles are written, but I'm going to do it kind of in the same way. I'm going to call this EDC, and E to D to C. Again, go down the short side, then down the long side. We could have also chosen, because the bottom two angles are equal, we could have also chosen DEC, right? We could have done it that direction. But again, both ways are totally fine here. All right. So another question here. So we've got two similar polygons. We want to complete the statement, and then we want to find the ratio of a side length in the first polygon to the side length in the second, right? So we're going to go first, then second, and we're going to write that as a proper fraction. Um, um, and again, that's what it says. Find the ratio of a side length in the first to the second. So that's going to have the the number and then another number, right? So we'll see it written that way with the colon, or we can write it as a again, it says as a proper fraction, 1 to 2 or whatever it is. Okay, so we've got VWXY, so V to W, W to X, X to Y, right? So if we look here, we can assume, because of the shape here, this is a parallelogram, that we have from V to W is 20. It's the longer of the two sides. So we go long side, short side, long side, right? That's kind of the same idea. So we're going to do the same thing here, right? So we're going to go from long side, long, short, long, right? So we can go in this case We could do the same bit here. We can do D to C, C to F, F to E. Again, there's a couple of other options we could do as well, but again, long, short, long, right? So I'm going to do here, I'm going to do D, C, F, E. And so how do we measure these side lengths? And how do we look at that fraction? Again, it says find the ratio of the side length in the first to its corresponding side in the second. So the long sides are 20 and 10. So this would be 20 to 10. We could also go short side to short side. This is 16 to 8. So both of these fractions can be reduced to 2 to 1. You could just write 2, right? That would also be fine. Again, because again, as a whole number, this would be a whole number that could simplify down. This wouldn't be a proper fraction. So we would write it as just the number 2. So just be careful there, right? It could be a fraction. If it can be reduced, we should reduce it. Okay. Let me zoom out just a tad. Okay, so the last couple questions we're going to figure out, are these similar shapes or not? So we're going to look here. We're going to look to see, again, are all the angles the same? And we have a constant ratio of sides as well? So I see in the first image, I have 54-degree angles. In the second, I have 119. All right, so that doesn't mean anything on its own. And what we're going to do is we're going to try and figure out, okay, what is missing here? So I'm going to look at my first figure here and say, okay, well, I've got in the whole shape, because it's a quadrilateral, there should be 360 degrees. Okay, so if I take away two 54-degree angles, so that's 54, and then minus another 54, how much is left, right? So this is 108 together, so I should have 252 degrees left over, right? So I have 252 degrees left over. Now this is being split into two angles, right? There's two additional angles. We've got a 54, a 54. Now 252 would be 126 and 126. Okay. Now this is telling me that this other shape has 119-degree angles. So this is a big old no. Right? They've got to have all of the same angles, even though the side lengths are all equal. These are different types of rhombuses, right? But one is kind of more squeezed than the other. And so again, because these two angles differ, we could have also done this from the other angles here, right? We could have looked from this one and figured out what angles remain and then compared it to 54, but we don't need to do that here. That's a no.